Hello, everybody. Good morning, good evening, good night, as the case may be. It's a great pleasure for me to introduce three scientists from India who are working on problems relating to quantum annealing and the use of this new exciting technology in the field of of medical sciences, in particular to the current ongoing problems that relate to the current ongoing pandemic of COVID-19. So today's speakers are Dr. Kunal, who's an assistant professor at the Department of Computer Science in Acharya Prafulla Chandra College in New Barakpur, West Bengal, India. Dr. Kunal has served as a reviewer for several SCI journals, including Elsevier Microelectronics Journal and the IEEE Transactions series, as well as many international conferences. He currently serves as an associate editorial board member of the current Chinese Computer Science Journal. His research interests include nano devices like quantum dot cellular automata, VLSI design, digital microfluidic biochip, and of course, as I mentioned, and of course, as we know, the topic today of today's talk, applications of applications of quantum annealing technology to solving problems in the real world. A co-speaker with Dr. Kunal is Asmita Banerjee. She has a BTech in computer science and engineering. She has worked on graph coloring quantum algorithms at the Indian Institute of Science under Professor P.K. Panigrahi. She has also worked on the nurse scheduling problem using quantum annealing, and this is going to be the talk for today. She'll be telling us more about that. And she is currently interning under Professor Madhur Srivastava at the Department of Chemistry and Chemical Biology at Cornell University, USA. And she's also involved in a project dealing with chirality of quantum states in the Department of Physics at the University of Warsaw. Our third co-speaker for today's talk is Arindam, and he's working towards his PhD on quantum technology. He's currently a visiting faculty member in the Narula Institute of Technology in Kolkata, India. He has written several international journal papers and several conference papers, and has served as a reviewer for many international conferences as well. His research interests include quantum dot cellular automata, quantum computing, quantum cryptography, analog and digital VLSI circuit design, and the application of quantum annealing to solve problems coming from the industry, and particularly COVID-19, as he'll talk about in today's talk. So those are our esteemed speaker for today. And I'll pass on the mic to them in just a second after I say the following. Please note that if you wish to ask a question or raise a question, please click on the Q&A button provided at the bottom of the screen, of the Zoom screen, and type your question there, and I'll make a note and pass it on to the speakers at an appropriate stage. So with that, I pass the mic to Dr. Kunal. Please go ahead and introduce the speakers and yourself, please.
Thank you, Dr. Faisal. Today, we are going to discuss about medical staff scheduling problem under COVID-19 clinics using the quantum annealing. In this presentation or in this panel discussion, first, the Asmita will discuss about the basic introductory part of quantum annealing and your quantum computing. Then I will discuss about the QUBO and some examples. And then gradually we will enter into the actual problem of scheduling problem of medical staff problems to the presentation. So I request Asmita, please take your mic.
Yes, sir. Sure. Hello, everyone. My name is Asmita Banerjee, and I'll be starting off with the topic. So as we know, our topic goes as mitigating scheduling of medical staff in a COVID-19 clinic by quantum annealing. So the first question that we raised or that came to our mind is, how can we arrange the roster for nurse and physicians during COVID-19 pandemic concerning their safety and working pressure? So we always had to keep in mind that there were certain constraints according to WHO guidelines and the COVID-19 situations that we had to maintain while we were doing the scheduling problem. And we proceeded with such constraints. But firstly, we implemented the entire algorithm using quantum annealing. So I'll be first speaking about the basic concepts of that. And later, Kunal sir, Dr. Kunal Das, my colleagues Dr. Kunal Das and Dr. Arindam Sadhu will be elaborating on the topics of the problem. So as the beginning goes, the basic framework of quantum computing, our problem was implemented upon. I would first like to tell you about the beginning of quantum computing. So we all know it, but it started with Feynman's idea that some quantum mechanical systems cannot be always properly simulated in classical computers. And to do that, we need exponential growth of resources. So we needed a quantum computer for that, and the journey of quantum computers started over there. Now, you can kind of imagine that, like we use GPU for better graphical instructions in the computer instead of a CPU, and that also processes information faster than graphical information faster than a normal CPU. A quantum computer also provides quadratically or polynomial faster timing compared to the classical computers. Now, in the next slide, we'll see that there is a history of the evolution of quantum computers, and it went on something like this. You can see the organizations and the number of qubits they used. And what we have used is actually on the right, bottom right, that is 2000 qubit processor, which was given by D-Wave. And that is the basic framework upon which we have been working on our problem. Coming up next is, so please next slide. Coming up next, we have the two basic approaches to the quantum computing regime. So number one is that the gate level architecture and the quantum annealing architecture. Now the gate level architecture has two kinds of, like here the picture is shown that there are two qubits and there's a flux bias and a tunable coupler. Now there is only one coupler here. And if you see, the flux bias actually does the computation using the coupler, and the readouts are actually where the outputs come. But if you see on the right side, which is actually the quantum annealing architecture, you can see that there are couplers which are represented by the pink dots and the pink square boxes, and the qubits which are represented by the blue dots. You can see that there are 4 connections here compared to the other one over there in the gate level architecture. So I'll be discussing elaborately in the later on slides. So if you go to the next slide, we'll find out that what is a qubit. Now we all know this is a quantum computing conference, of course, but this is again to tell that quantum qubit is a quantum mechanical version of a classical bit. Now this is the basic building block of quantum computers, and you can say that they exist either in the state 0, 1, or can be also in a superposition of both. Now, if you have noticed in the previous slide that we can also use those couplers and qubits to actually, to manipulate them using the superpositions. So that is where the quantum computer provides an advantage over the classical computers. Now, going on to the next slide, to actually compare the circuit model and the quantum annealing architecture. Now, the circuit model is the universal gate model. It is basically a qubit which can be represented by or mapped to a block of qubits. Now, these block of qubits, this particular qubit, they can be in logical states of, their physical states can be manipulated and they can represent the logical states accordingly. Now, these building blocks or these blocks of qubits, they are connected by a logical gate, which actually carries the information or the propagation of information, and they can manipulate the qubits and give a desired output so that we don't go on to some other qubit and they have a proper connection maintained. Now, this is something which we can use to implement Shor's algorithm, like which is used to break the RSA cryptography, or Grover's algorithm for fast search. And to be honest, to develop circuit model, we have to be very sure that we develop the chips very perfectly, so that there is no decoherence. So this is the first thing that is a challenge of the circuit model. Now going on to the next, adiabatic quantum computing, you can see that the adiabatic quantum computing is totally based on the Hamiltonian of a physical system. The initial Hamiltonian gradually evolves to a final Hamiltonian by maintaining the ground state. And this ground state of the final Hamiltonian is actually the solution of the optimization problem, or the problem which we implement upon. Now, going on to the next slide, the formal definition given by, next slide please. Now, the formal definition given by Born and Fogg based on the adiabatic theorem was as follows. A physical system remains in the instantaneous eigenstate if a given perturbation is acting on it slowly enough and if there is a gap between the eigenvalues and the rest of the Hamiltonian spectrum. So it is kind of in layman's terms what I described previously. So this is a more formal definition and in mathematical terms. So if we go on to the next slide, we can see that what quantum annealing is mainly about. Now, quantum annealing is a type of heuristic search algorithm that can be actually implemented in the AQC platform or the adiabatic quantum computing platform. So you can say kind of quantum annealing inhabits a regime that is intermediate between idealized assumptions of universal adiabatic quantum computing and unavoidable experimental compromises. Quantum annealing works best on problems where there are potential solutions, and a lot of potential solutions, and ideally we have to find a good enough or local minima solution, something, and we can implement it in something like scheduling. So it goes as we have a lot of solutions and we have to gradually find the best solution of them all, and that is where quantum annealing or adiabatic quantum computing framework of it actually comes into play. And we actually decided to use it for our problem because we thought that this is the best platform to use it. So this is the basic about quantum annealing. If we go on to the next slide, you can see the description using the quantum tunnels. So this is the description basically. So if you ask me about the difference between what quantum annealing and simulated annealing would be, we could go on to the next slide, and I could there's a note that there's a latest announcement from Google that says that D-Wave machine is faster than simulated annealing running on a single core. So quantum annealing is kind of an advanced alternative to classical simulated annealing. Now, what is classical simulated annealing? It is an approach to solve optimization problems where the cost functions are denoted as energy functions. Now, in case of that, we have to gradually go from one minima to another by thermal hopping. But in case of quantum annealing, we can actually use the quantum mechanical phenomena that is available to us, like tunneling and entanglement or superposition, which can be used, and we can in case of narrow valleys or in case of narrow barriers, we can actually find some good use to it. Also, you can say that in case of simulated annealing, it's worth noting that it might have some advantage when the barrier is wide and shallow. So these are the though quantum annealing and simulated annealing have some huge similarities between them, but there are also these kind of differences. Mainly the difference that quantum annealing uses the quantum mechanical phenomena, which is actually the fruitful, the result which we used in our algorithm. Now, in the next slide, we will see that for D-Wave, the basic scheme is as follows. So we use the system, and first the computational problem has to be mapped to a corresponding physical problem, where the cost function is presented by some Hamiltonian of the Ising form. So we actually basically form a Hamiltonian and we gradually map it to a Ising form, and we implement the problem. We gradually evolve the Hamiltonian and we see where the cost function is. So the qubits are coupled together using programmable elements, which provides an energy that is continuously, aligning or not aligning in anti-alignment respectively with the couplers. So the basic behavior of the system can be described with an Ising model Hamiltonian. We used a similar one in case of our problem, that is now scheduling problem. So coming up next will be Dr. Kunal Das, who will be describing more about how we have actually implemented the problem using the constraints and forming the QUBO and the Ising models. Thank you.
Kunal, please unmute yourself.
Thank you, Asmita, giving the introduction about the quantum annealing and simulated annealing. So I hope that the difference between the classical and quantum annealing is understandable. And what is the advantage in case of quantum annealing have, and how we can utilize or explore this advantage in solving a problem. So there are several problems you can see here. We will discuss both the problems. One is basically logistic problems, which the very large dimension of logistic problems. In case of logistic problems, idea is that the packet of assignments will be delivered in a minimum time. And second one is our problem, which is a nursing scheduling problem or medical staff scheduling problem during COVID pandemic. In a COVID pandemic, what is that? In a COVID pandemic, there is a more constraints we have. So we have a large number of variables because a large number of doctors, large number of nurses, but at the same time we have a large number of constraints also. So what is our target? Our target is to get the optimal scheduling for that problem, such that the all doctors and nurse can be relaxed mostly the times if the scheduling is such a way. So in a clinic, there are maybe the thousands beds. So you can think about that how many number of nurses and doctors are required during this COVID pandemic situations, and the scheduling by classical computing is become very critical for that problem, because you are not able to get some optimal solution for that, such that the doctor or nurse can get a better relaxation from that from their work. So obviously you have to follow the some WHO guideline as well to maintain their scheduling as well, because you can't allow more than 8 hours. You cannot allow the repeated schedule, uh, two slots a day, uh, because their health also concerned, because they might be, if they are utilized much more, then they might be infected. So all the part should be taken care during this scheduling problem. So now I giving the idea about by using the example of different optimizing problem in case of classical computing as well as in the quantum computing. This is called a constant optimization problems, and there could be a problem like you can say that the facility location problem, which is the quadratic assignment problems, job scheduling problem, which is the satisfiability problem. You can say the satisfiability problem Sudoku. There is a constant satisfiability problem, map coloring, that the interquadratic models. So all are basically optimizing problem. In optimization problem, you can see These problems are solvable in classical computing as well. But what is the problem is that if you can see from Asmita's lectures that you can start into the local minimum. If you have using the simulated annealing, for example, an algorithm, then you have probability to start in a local minimum. So then, in a classical computing, what you getting the minima that is not an actual minima you are searching for. So you are not getting the exact or optimal result for that problem. So if you run the same problem by using a quantum annealing or by a quantum annealer, then you will be able to get lower minima as well. That is, you can say that you get the global minima. So that is the advantage we are looking for, and how we are modeled the problem, that is will be discussed here. So how we will model a problem? We can model a problem. Suppose we have taken a one assignment problem, that is a logistic problems. So we have a assignments that package, assignment packet or packet to be delivered to a particular location by a vehicles. Accounting the times and vehicles capacity, you have to send this uh, um, packet to the destination. So what is the dimension? The dimension become the number of locations, number of vehicles, number of time intervals, capacity of vehicles, and this as a sum, as a multiplication of these four, it become the entire number of variables of a problem. So now the what are the constants? The constants is that vehicles cannot arrive two cities simultaneously. It is obvious because one vehicle cannot be present in a two place simultaneously. So this is obvious. You should not consider that one vehicle should be available in both the places simultaneously. That is not possible. So this is the constants. And vehicle can only arrive a location at once. So one vehicle can arrive a location once. So that means each and every vehicle must go by their Hamiltonian circuits. So they must follow the Hamiltonian circuits. So each and every place will be visited once. It cannot visit multiple times. So you must have a Hamiltonian cycles. So that means you thinking that this problem become the NP hard, right? Now the vehicles arriving at a location once only, and only one vehicles will arrive at one location. So that means if you have a three vehicles, the two vehicles cannot arrive the same place. So only one vehicle will arrive in the one place. So if you have an entire circuit, so if the entire circuit, then you must follow that some vehicles will cover the some cities, some vehicle will cover some cities, and some other vehicles will cover other cities. So as a result, you can see that if you have a large your business area, then your problem size will become 9.6 million variables. So is it's a very huge problem size to solve in any by any classical computers. Uh, and definitely the question arises whether it is now suitable to fit in our current quantum computer as well. If your problem size is like 9.6 million variables, that is still not possible to fit in our current quantum annealing based quantum computers. That is like for example, for DOF 2000Q, that is not possible. Maybe the further they're improving their number of qubits, then this space can be available. But our target is what? Our target is that scheduling will be such that objective will be that is the minimizing the time of delivery, right? So we want to get the minimum time of delivery of a packet. So now what is the idea? We have entire landscape of energy spectra, right? So if we calculate a system the entire landscape at a time. So can we say that which one is the minimum? So there can be the so many red dots here, and these so many red dots, among them, one of them will be the minimum. Now the classically, what is your approach will be? You will be finding some red dots as your minimum results. So because in your energy equivalent, that will be the optimal solution. So in that classical environment and quantum environment, that the practice is that you are either you are doing the simulator only, or in a quantum you are doing the quantum handling. So in that scenario, you are just going to get that which one is the local and which one is the global, right? So that is another approach of solving the problems. This is a heuristic approach. Is called QAOA, quantum approximation optimization algorithms that you can apply, and that is mainly the cost function based Hamiltonian to finding the near optimal solutions, or the mixing the Hamiltonian to enforce the focus on feasible solutions, right? So this is the approach of solving the problems. Okay, so you are cost function based Hamiltonian, you are calculating some cost function based Hamiltonian, and from that you are getting the which one is the minimum cost or minimum value or minimum energy, as you so know that ground state energy, which one is the minimum ground state energy, that will be your optimal solutions, right? Uh, Obviously, sometime might be that quantum computer fails. That might be the possibilities that you are not able to get actual minimum. That also obvious. Sometime the different quantum computer may give the different performance. Now this is the programming model. If you see that the qubits are which are connected with a coupler. Basically, the one qubit influence the another qubit. So in a Annealing cycles, the qubits are participants, and it is actually settled with either 0 or 1. As you can see that the one video is given in our presentation, that 1 is becoming 0, 0 is higher energy, or 1 is lower energy. So that means that qubit is going to become the lower energy level for 1. So that is actually sensing that that qubit is a 1 state, right? So this is the process of annealing. If you have a 50-50, so then it is the chance of 50% to be the 0, 50% to be 1. So this is the influence, and that influence is done by a coupler, right? That coupler is a physical device that is connected between the qubits, right? And that actually influence that couplers. Now the what is weight? As the two coupling one way coupling system with the two qubits, there are a bias. So this bias is basically some weights, and you can say that the BII and BIJ, this is the weight and strength, which are actually controlled by controlled by a programmer, and that will be giving that objective and objective functions in the during the annealing time or annealing cycle, that function to be minimized. So objective is a Bij over Qi, the the that is the weight over Qi bit, equals to the summation of all Bij Qi, Qj. So that is the influencing part of that part. So, and if this the objective is to minimize that, so that the system sample of Qi that minimize the objective, that actually will be minimize the objective. So this is the model of programming. Now we are gradually moving towards that how this problem can be summarized. If you can see that these are the variables, capacity, numbers of locations, number of vehicles, and number of intervals, all are our variables, number of variables, which are the input of a problem, right? So from that, you will get that a uh, vector, right? You will get a vector, and from that, you will, suppose you want to construct the Q matrix. And this Q matrix will be solved by some QB solver, and QB solver for assigning such a QUBO. So from a QUBO, you will get that QB solver, and a resultant solution will give you that lower energy Hamiltonian, right? Now let us see that what is you can say that by means of combinatorial optimization problem in case of QUBO optimization. It's basically the variables which are considered as a true and false states, and from that you will develop the quadratic unconstrained binary optimization problems. And for different examples, not only for these examples which we are discussing currently, like your assignments problems, that is your logistic problems, or scheduling problem for nursing, you can go for making a team of n number of players. So if you have a n number of players, you want to make a two teams from that team, so that you can have a n by two for each team. So you can develop a QUBO for that, and you can solve it by applying our quantum computers. Now, how the QUBO can be developed, we can see that as X is a vector of binary decision variables, and now XT is this transpose matrix of that, and Q is a squared matrix, or you can say the Q matrix, for instance. Now, how the Q matrix can be developed? Q matrix is basically a symmetric matrix, and you can form the Q symmetric forms, or you can form in a upper triangular forms. If it's a symmetric forms, you can see that this is a symmetric forms. You can see that only the diagonals remaining, all the parts are symmetric. So this is the Qij and equals to Qji. So if you want to convert into, if you want to convert this symmetric matrix to upper diagonal matrix, just doing that Qij plus Qji divided by 2 and putting that portion is a 0. So as a result, what you get, for example, this is the just the upper triangular matrix for the Q matrix, right? So this, once you get this matrix from your QUBO, so you are giving this matrix to your quantum computer. There's a quantum annealer. So quantum annealer will give you the minimum Hamiltonian of that possible solutions, right? For a given problem. So in our case, rest of the part Arindam will discuss that how this Hamiltonian minimum Hamiltonian is achieved from designing QUBO to the Q matrix. Arindam?
Arindam, if I may raise a few questions that I'm seeing on Q&A before you take over. Would that be okay?
Okay. Sure.
Okay. So I have a few questions here. First question was about an implementation code or use case for this problem. So you guys have some code for, I suppose, is a question that is available, open source or something.
Yes, you can if you require the codes, that is that can be available already. It is available in GitHub. You can go from that. Is it about the just coding? You want how to code it? Yes, that is available in our GitHub account.
Right, I think that addresses the question. It was basically about implementation code or use case. So the answer is that it's available on GitHub, but you can always get in touch with any one of the speakers, I suppose, and request it. Would that be okay, Kunal?
Yes.
Wonderful. So two more questions really quickly. I'll raise this one first. The question was about the term mixed Hamiltonian. Could you please elaborate?
Yeah,
So Kunal, I think you
mixed.
used that term.
Yeah, mixed Hamiltonian. I want to say what is that. One thing is that you are getting minimum, right? So one is applying the minimum Hamiltonian, and sometime you what you doing, you are getting that the energy spectra, and where is the minimum energy spectra. This is the minimum Hamiltonian, right? So this in that case, we are calling that the summation of both the entire system Hamiltonian is called as a mixed Hamiltonian.
All right, wonderful. And the other question was from Amol. It says, out of curiosity, can same problem be solved by IBM-Q?
One thing that IBM-Q is not a quantum annealer. IBM-Q is a gate level quantum computing. Gate level quantum computing is a practice to solve the problem by gate level computation, or algorithm is quite different, because you cannot use the Ising model or QUBO models over there. You have to code it, or you have to make it your algorithm only on based on their gates. So that problem can we think about, but that the size of qubits is not sufficient one for solving these type of problems.
Excellent. Thank you so much. There are some other questions. Two of them are about the GitHub link where the code is. So if you can share that, we can ask Vikas to post it here.
Okay, surely I will share. And one thing that if you want to please just email me kunal@apccollege.ac.in. I'm writing in a chat box my mail ID. It will be better. So please just put a mail. I will send the link or directly the.
Wonderful. And one last question before we move on to Arindam. It relates to what you had said, Kunal. With regards to coupler and strength, could you please elaborate? And I think they want the one person asking the question wants this to be addressed in the context of teleportation, interference, and tunneling, if possible.
Yeah. Yes. Coupler is what? The two qubits. Suppose the two qubits are independent. So then there is no way of influencing each other, right? So if there are some connecting media, some physical devices there is called a coupler. And then the situation comes then that the one qubit can influence other. So if the one qubit can influence other, then the two qubits are not independent. They are somehow connected, right? So whatever the changes took place in a qubit, you actually compute that. Okay. So when you measure the qubits, the energy spectra, whatever you actually measuring, that is the changes of qubits you are measuring. So once it is doing, definitely it's a interference you are taking place. You are making the superposition of these two qubits. You are maybe for entanglement, what you are doing, that's you are doing the teleport. In case of teleportation, you are doing entanglement of two qubits uh, with some computing by some if in case of gate level quantum computing, if you make a spin of able to make a spin of a electron such a fashion, and they are tossed to together, and they will be either 0 0 or 0 1 or 1 1, right? So they because they are connected. And if we able to toss them, then what will become? If both will be either zero, both will be either one, and if you twist them, then it's a zero one, right? So this is the part of their strength and coupling.
Excellent. Thank you, Kunal. With that, we'll hold on to a few more questions that have come up until the end of the presentation by Arindam. So Arindam, I give you the mic. Please continue the rest of the presentation.
Thank you, sir. And thank you, Kunal sir and Asmita. In my part, actually, I'm presenting here the implementations of the QUBO and the Hamiltonian functions for implementation of the nursing scheduling or nurse physician scheduling problem. In this slide, we are just mentioned about the flow of work, how we will complete our work. The first one is the constant. We will discuss about the constant, that is the hard constant or the soft constant. Secondly, using the constant, we form the objective functions or the Hamiltonian function in Ising model, or actually in the QUBO model first, then we convert to the Ising model. Then we are using the, after completing the model, after designing the model, we scheduled the optimizations for the quantum annealing for individually. First we are completed, that is nurse scheduling problem individually complete, then PSP for the physician scheduling problem, and then finally we complete the total Hamiltonian function. We form the total Hamiltonian function for the NPSP, that means the nurse and physician both or at a time, because we know that one in this scenario or in this pandemic situation, nurse and any health worker are the frontliner. So that's why we are taken here for the nurse and the physicians or the doctors, and to as a main part, and that's why we will discuss in the next slide about the constant. And so first, the next slide, please. So here we are discuss about the different constant actually. So before that, we already mentioned in the last slide, we first complete the NSP, that means the nurse scheduling. PSP is the first scheduling problem or the physician scheduling problem, and then the NPSP cumulatively with deal with the creating the roster for both the nurse and physicians according to the some given constant here. So here we set the 4 shift per day, and that is the morning shift or morning time, and the daytime, then early night and late night. That means we divide the 24 hours. Previous slide, please. That is the then we divide the total day in at four sections. So that is mentioned as the morning time and daytime, early night and the late night. And each shift consists of the 6 hours. So for the specified number of day, we are just doing that here. So what we are doing, that the first one, the first constant, due to the overload of the working shift, we set our first constant, that is the constant 1, as a hard constant. So that means the maximum number of shifts that each nurse or each physician can work per day. So as to ensure that nurse or the physician or any health worker can take the sufficient amount of rest in between the shift. So due to the high pressure working environment in ward actually, so we set the second constant, and that is our soft constant we are taken. That each nurse or each physician can do at most 2 consecutive shifts, not more than 2 consecutive shifts in a day. That means in a day there is a 4 shifts there, but each nurse or physician can attend 2 shifts in a day or in a single day. So according to the WHO guideline, so maintaining the distance between individuals is extremely important to mitigate the mitigate to spread the virus of the COVID-19, even in the frontline medical worker also, because they are too much important for us. So hence we said our third constant, and it is also the hard constant. That is to another hard constant, that is because first constant is another hard constant, and this third constant is also one hard constant to maximum the number of the nurse or physician that can present during in each shift. So these are the constant. So if we are discuss about the briefly about the first constant is our hard constant, the maximum number of shift each nurse or each physician can attain per day. And second constant is the number of consecutive shift by the each nurse or physician can, that is in a day, that is soft constant. And again the third constant or the hard constant of our case, that is the maximum number of nurse or physician or in each shift can have. So next slide please. So for the combinatorial optimization problem to solve, because Kunal sir and Asmita both are presented that one, that for combinatorial optimization problem to solve on quantum annealer, it is the best practice to formulate it as a QUBO first, that means the quadratic unconstrained binary optimization, and then we just convert to the QUBO into the Ising formulation or Hamiltonian Ising formulation as the input of the D-wave annealer. So this is the first constant. We are using the first constant. We form the Hamiltonian for denoting the H1 is the gamma in summation of n belongs to the 1 to capital N and S belongs to 1 to capital S, HQNS minus B whole square. And the equation according to the QUBO formulation we just mentioned in the equation 1. In this equation, the first one is called the gamma, is the Lagrangian constant, and it is defined by the programmer to tune the function more. And here in this experiment we are taking as a gamma is a 5. And the second part is coming, that is the small n. It is the number of knots is attained in the specific time or for the specific shift small s. And the small n belongs to the 1 to capital N, and the shift, this is denoted by the small s, belongs to the 1 to capital S. Now another part of the important to formulation of the QUBO of using the constant 1, that is the HQNS part. The H part we just mentioned in the before last slide, that each shift duration is the 6 hours, and that is the H, and total duration of individual shift. And QNS is the part of the QUBO, that is 0 or 1 or the binary formation of the QNS. And so if any knots is present for a specific shift, at that moment QNS value will be the 1. Otherwise it will be the 0. That means that at that moment any roster is not working properly. Now, and the third part is called the B. Here B we just mentioned that one, that each knots can do maximum 2 shift. That means we already mentioned that each shift duration is 6 hours, so 2 shift is 12 hours. So that's why this is indicated that B is equals to 12. In equation 1, we just mentioned that formulation, that is the gamma H square minus 2HB QNS part. These are the part of the diagonal, and off diagonal part is the Q2H square part for the Q matrix formulations. So in the QUBO formula, because Kunal sir has already mentioned that one, that in QUBO formulation, X transpose Q and X part are there, and the Q is the in the normal formulation in Q, that is the Q matrix, and that Q matrix will be formed by these equations also, or equations value. The first one is the diagonal, and the gamma 2H square is the part, is the off diagonal part. Next slide please. Sir, next slide please. And for our second constraint, this is the soft constant. We take the composite indices, that is the I of ns and j of n of s plus 1. J of n of s plus 1, and the binary part, that is the qns and qns plus 1. Actually, the I of ns and j of ns plus 1 as a function of number of nurses and slips, and hence with the QUBO functions of the objective QUBO objective function to form our constraint, and that is at most 2 consecutive shift, which we are trying to impose that one, that is indicated by that INS and S plus 1 for J part, that indicates the consecutive part of consecutive shift to maintain that one. So in this part, we have just mentioned that one, that is C, that is the constant part, but actually it will becomes at again 0 for whenever we just mentioned that Q of NS, it is applicable for I of NS, and Q of NS plus 1 part, it is applicable for J of J n of S plus 1. So if any node is not attained consecutive state, so at the moment anything, that means the Q of n of S plus 1 will be the 0. So at that moment it will be the 0. Otherwise it will be the constant value that is indicated by the C. So next slide, for the constant 3, we are discussing about the third constant, that is one of the odd constant is that one, that is we said the total number for the hour of each shift can have, and combining the all nurses working hours are placed here as a small a we are indicated here. Small a is equals to h into m, where m is the maximum number of members that can be present in each shift, because we already mentioned that one, the constant 3 is the hard constant of our case, and the maximum number of nurses, that is also applicable for the maximum number of physician can take present or can present during the each shift. Here the same way, just like the constant 1, we just formulate the QUBO function and denoted by the H3. And here we have just mentioned the Lagrangian for the lambda, and these lambda's value we are taking as a 1.22 around. And same way, the small s is also denoting the number of shift or the shift, and which is belongs to 1 to capital S, and the small n, this is the number of knots here, and this is also belongs to 1 to capital N. And the H part is the same way, is the just like the constant 1, that is the total duration of a single shift, and that is the 6. And here we have just mentioned that is QNS. This is also the binary or for the QUBO formation, that is 0 and 1. If anybody is present, so that means at that moment QNS value will be 0. 1, otherwise it will be the 0. Now the constant term A is coming, that is A is equals to H into M, we just mentioned that one, and M is the maximum number of knots that can be present in each shift. And the lambda part, that is the Lagrangian constant, again the same way, just like the constant 1, we're just using, and this is totally user defined or the programmer defined, and we are using to tune our function more. And in this case or example, we are taking as the lambda's value is equal to 1.22. Next slide, please. So first one, we are just cumulatively, we are just mentioned that for the NSP problem, there is a not scheduling problem. We just individually in the last 3 slides, we mentioned individually the constant 1, constant 2, and constant 3. And in this equation 4, we just mentioned the cumulative way, that is the first one for the constant 1, and second one is coming for the constant 2, and third one is coming with the constant 3. And using this equation, whenever we are giving this as an input to the DWeb, we just convert to the Ising model as an input in the DWeb system. So we can easily calculate we can easily optimize our result. We can see in the next slide also. The next or the fifth equation we have just mentioned here for the physician scheduling problem. The first one is the gamma, and in the place of n, if we compare this equation with the 4, we can get only one difference. That is in the place of n, we just put the small p, and this small p is indicated for the physician, and each and every constant are the same. So just cumulative way, we just mention that one. That is for the constant 1, we just form our QUBO, and then second, and then third, and cumulatively we just mention in the equation 5. And for the same way, we can form also the Q matrix for this Hamiltonian for the physician scheduling problem. And another important point, that is the small p, that is also we just mentioned the number of physician that is present in our hospital, and that is belongs to 1 to p. Next slide, please. So here we will discuss about the nurse-physician scheduling problem. That means in the last slide we already discussed about the individual for the nursing, and at the same time we will discuss about the physician individually. Now we know that one because in hospital, nurse and physician both are important and they work as a team. So here we take this one as a team member, and in this example, we just mentioned in a cumulatively way, and in this equation, we just, if we differentiate with the equation 4 and 5, we'll get the difference only then the small t. Otherwise, each and every shift is equal thing. But in this team, some number of, or the n number of nurse and p number of physician are present at that moment. So that's why we just mentioned the t, and this is the t is the nothing but the team consists of the nurse and physician, and they belongs to the 1 to capital T, and small s, that is belongs to the 1 to capital S, and it is denoted the number of shifts. So first one for the multiplication form of the gamma is just for the constant 1, and second part for t equals to 1 to capital T, and the qi of j, that is for the consecutive shift for the soft constant part, and the lambda part is our third hard constant, or third constant, that is also our hard constant. So in this scenario, or in this example, we are taking this one as a QUBO formulation. Then we just give it as the input of the Ising formulation. And we already mentioned, Kunal has already mentioned that one. If you take our program from the GitHub, so you will understand that one, how I will just give the input to the Ising. So in the D-web, so you can understand that all of us is clear to all of us. So now in the next slide, if we are discussing about the configurations part, that is we just mentioned that is the B is equals to 12. That's why each nurse or each physician can do maximum 2 shifts in a day. So as we are taking that one, so in 7 days, that will be the 14 shift are there. So here we are taking only 12 days, because in 7 days, 1 is off day and 6 is we are taking as a working day. So that's why we are taking the maximum 12 shift. That is the constant 1 we are taking cumulatively way, and the constant 3, that is the each shift maximum 2 nurse can avail. That is we are just mentioned in each shift in single word, the maximum number of nurses can present is the 2, and maximum number of physician can avail or present is 1. So in team formation, we just mentioned in the next slide, that is in nurse, number of nurse is 2 and number of physician is 1. So in this configuration, we run our model in a first simulator, that is the classical way, and then we convert it to the forward and reverse annealing method for getting the resultant or the roster or the ground state energy of the comparison purpose. That according to our requirement, or our requirement meet or not, we will get in the resultant. So before going to the result, we already discussed, Asmita and Kunal sir both mentioned about the annealing part. And according to our here, we have just mentioned the reverse annealing, and in this process, the first one is coming as a starting from the reverse annealing, starting from for the s equals to 1 to s equals to from s equals to 1, and the reverse annealing is starting and towards to the maximum way we are getting around 4 or around 4.4, and then it will stop or the for pause for 80 around 82.33 microsecond. Then again it work for the forward annealing. So in this process, the first line, whenever we are if we are taking the extreme left downward from 1 to 0.5 or around the 0.5, so it will the reverse annealing process. It is starting from that point. So if we are getting exact value, so we can discuss about that one, that is around whenever we're talking about the to process, that means for the reverse annealing process, and that is starting or continued for the 2.75 micro second, and annealing parameter is the 0.45 actually, or around the 5, and again it is paused for the 80 for 83.3 microsecond, and again it comes up to the 1 and for complete the forward annealing. Next slide please, sir. Next slide. Now, here we are discuss about the result and escalation point, because we are already mentioned that one that we are taking that the 4 NORs for the 12 shift. That means we are taking in total for 12 shift for that means the we are considering the 3-day, and here we just mentioned the 2 hard constant because we mentioned in the last slide that is fixed. That means in the 7th day, that is off day, that's our soft constant part. And here we are taking in our example 4 NORs are present in our example part, and as per our first and third constant, we have just mentioned that individually each NORs can avail maximum 2 shift in a day. And so the A part, or if we consider on the figure A, so we can think that one, that is the 1, 2, 3, 4 belongs to the first day, then 5, 6, 7, 8 is the second day, and 9, 10, 11, 12 is the third day. So we can see whenever the first result is come out for the simulated annealing part, and in simulated annealing part, we get that one, that a single NORs working for 3 shift, the first one. And more than one, the second NORs we are getting, that is the second NORs 2 working consecutive 4 NORs. That is also violate our constraint. That means in simulated annealing, we are not getting the proper result, or we are not meeting our constraint properly. So whenever we are taking in the forward annealing part, so at that moment, it's a very straightforward results we are getting. And so at that moment, they are getting the specific gap. So if we are taking result of the reverse annealing part, at that moment we can see the difference in output. That means each and every NORs maintained, or that means every result get our constant properly. That means if we are taking 1 to 4, that means first day, so at that moment each and every NORs, that means the NORs 1, NORs 2, and NORs 1, NORs 3, and NORs 4, they are doing maximum 2 shift. But in the case of the NORs 2, the NORs 2, that the consecutive 2 shift are attend, but the first constant part, that is maximum 2 shift can attend per day, that will miss in our part for that case. But otherwise, if we are taking, or if we consider, if we are compare with the other part, then we can find out that this result, or the reverse annealing part, will much more effective result we are getting. Next slide please. So these results are comes for the team purpose, that is for the individual. That means we are taking here as an example is the 6 nurses are there. Previous one. The 6 nurses are there, 2 doctors we are taking. The first case, always we are taking the 2 hard constant for getting the optimized result. And individually, we mentioned that one, that each in each shift 2 nurse, maximum 2 nurse, and a single doctor can attend that one. So if we are taking example for the simulated annealing, that means the figure 1, we can get that one, that is maximum time in each shift, maximum 2 nurses are present. But for doctor case, this is also meet our constant properly. But as the doctors are 2, so the original result or our expected result are the consecutively, if they attend the if they attend the consecutively, that will be the much more effective one. And if we consider the last 3, that means 18, 19 and 20 shift, then we can we can see that that is the doctor 1 consecutively attend the 3 shift, that will not meet our constraint. So that's also problem. So whenever we are taking the output from the forward annealing, that means if we are concentrated on the figure B, so we can think that we get that one, that is maximum time we meet our constant, and at the same time. And but for the doctor case, if we think that if we see here for 8 and 9, so at that moment we get that one, that is doctor 1 consecutively attend 2 shift. So if we are getting in, or if we consider it on the figure C, so at that moment we get that our constant meet each and every constant meet properly. That means the each shift 2 nurses, they also meet the they attend the consecutive shift. And for the doctor case, they are maintaining properly, they are getting one gap in between per shift, and they are attend consecutively. That means first one doctor 2 is attend, then doctor 1. So in total time or total duration of the 3 days, we are getting 5 days, sorry, in this 5 days experiment result, we getting that one, that each and every constant we are properly get the output. So from that point of view, we can easily understand that one, that the simulated annealing or the classical part, from the classical part, the reverse annealing gives us the much more result, because here the number of nurse is very fixed or very low, that is the 6, but or doctor number of doctor is also 2. But whenever we consider a big hospital, so at that moment number of nurse and doctors will be much more higher than the other. So at that moment we get the much more result in annealing in respective to the simulated annealing. So next slide, please. So next slide. Here in this slide, we are just comparing our result in simulated annealing, forward annealing, and reverse annealing. This is the y-axis belongs to the ground state and energy for the simulated annealing, forward annealing, and the reverse annealing. First of all, we are just mentioned our soft constant as a middle priority and the high priority. The constant values or tangents values, if we fixed as much more higher than the space, that means if it is higher priority, then we are taking as a 2, and middle priority we are taking as a 1. So at that moment we will get that one, that the middle priority and the higher, for the higher priority, reverse annealing always gives us the better result, because we know that one, that the ground state energy will give us the most output for the for the simulated one. And here in this figure we can easily identify that one, that the reverse annealing always gives us the better result whenever we are giving the prior soft constant, giving we are giving the priority for the soft constant. So in the next slide, we will discuss about the conclusion of our project. And this here we are in this experiment, we presented the non-physician scheduling problem, specifically for the COVID-19 pandemic situation, and the proposed Hamiltonian function for the nurse scheduling problem and the physician scheduling problem, and cumulative way, that means the nurse and physician scheduling problem, are reducing the QUBO model first, and then we just transformed into the easing model to give the input in the DWeb 2000 qubit annealer. Now, it can be observed that that off constant is partially satisfied if we are taking two hard constant in our experiment, because we understand that one, that is if we are taking 6 days scenario, so 7 days is automatically off. And at the same time, we can take an example another way, that is if we are doing 15 days constant work, and after about the next 15 days of a month will be holiday for that group, that will be much more also benefited, or another can see that one. So in this experiment, we can easily understand that one, that is for the reverse annealing part, we will get a much more better result. And at the same time, these QUBO functions all are meet our constraint properly. So our will assure a rotating the safety of the COVID-19 frontline workers, not only for the nurse and physician. We can also bring this Hamiltonian function for the different frontline workers, so to maintain or to ease out the pressure among them. So before concluding that one, we can next slide. This work has been noted by, this is our team members, Dr. Kunal, Dr. Faisal, Asmita, Banerjee, and Sadhu. And before doing that one, this work is really thankful to the DWeb that allowed us to use the commercial DWeb 2000Q annealer to work COVID-19 specific scheduling problem. It's all. If anybody have any queries.
Right. Thank you so much, Arindam. That was excellent. Very detailed and meticulous presentation of the work. Thank you, Asmita, for your introduction and to the work, and Dr. Kunal for the introduction to the process of quantum annealing. There are a few questions, quite a few questions actually, that are here. I would like to share them with you so you can address them. I guess I'll start with the ones that are most relevant or closest to what Arindam just talked about. One of them has to do with the latest 5,000 qubit version of D-Wave's machine. So the question is, has this problem or algorithm been implemented in the D-Wave's latest 5,000 qubit quantum computer?
No, actually we are working on the D-Wave. We are not using 1,000 qubit because the access to use only 2,000. Hello.
We have only access of D-Wave 2000 Q, not the 5,000 qubits.
Excellent. There's another question here. This says, would it be safer with less exposure to have the same care teams work together? So I suppose that's kind of an interpretive question, like, you know, based on the results you have, how do you interpret that, right? So one of the interpretation would be, would it be safer to have the same care teams work together with less exposure?
Yeah, one thing as per WHO guideline, every 15 days, the entire team will go for leave for next 15 days because there may be they may be exposed but by the infection, right? So they are actually in a quarantine for next 15 days to reduce their infection rates, or maybe the chances of infection rate can be reduced. So the team is divided such a way that if the team one is working and team two is working in alternative fashions, suppose, then team three and team four are in a quarantine for reducing their infections, right? So, and another case is that to reduce the infections, you cannot allow more peoples in a world. That means you cannot allow the more number of nurses and more number of doctors. So that is also the case that you are reducing the infection rate, because that will create a distance, right? If you are consistent with the number of nurses and doctors, so then automatically it will be a chance of having the infection rate or infection rate can be increased. So there is two things that WHO has given a guideline that you can't use large number of nurses and doctors in a world, and after 15 days you have to give the mandatory quarantine for their saver.
All right. So here's another question about materials requirement planning. That's, I think, what MRP here stands for. And the question is, in terms of MRP and scheduling, MRP planning, materials requirements planning, and
Exactly.
scheduling. Do you think the
The
problem
same.
would be a good candidate for annealing?
Yeah. That could be formulated by QUBO and Ising models, and that could be a good application to solve in a D-wave quantum computer. A good idea.
Well, the interesting part was of this question is that a good candidate, this problem for annealing, or is it going to be overkill?
It's actually every research you have to search for it, whether the classical result is the best one. You might have some, for example, if you take uh, some searching algorithms. Okay, if you don't have better algorithm in a quantum computer, why you go for the quantum computers? Because quantum computers can't replace the entire classical computers. If the solution is the best in the classical computers, then go for it. Why you don't require to go for quantum computer? So you have to go for searching, doing the work, and if you get the better result, then okay. Otherwise your entire one thing you should find out that from that research, that you can say that no, for that problem the quantum computer is not a good. That is your outcome. So if you do that, nobody will try to get that into the fact. Okay. So I'm coming to the point of the filament, invention of filament. These are the material is not suitable for filaments, right? Even here is also tried whether here can be a material for the filament. So this is the list which are the not suitable for the filaments, right? So this is the same practice for the research. So you can find out that this problem is not suitable. So that is also a good result you are getting.
Great. Thank you, Kunal. And let's see a few more questions here. We have time. So one question which is interesting, I think, is about the direction of annealing. So the question says, which direction of annealing makes sense to go with? Would one just pick a constant direction? So this has to do with the reverse forward annealing.
Yeah. The question is probably the whether the reverse tunneling or a forward tunneling. Reverse tunneling looks better in terms of ground state energy levels, right? So if you show that our results and scheduling outputs, the energy level in case of reverse tunneling is lesser, and the scheduling also satisfied all the constants. So we proposed that the reverse annealing will be good for that problem.
Thank you. Here's a question which pertains to, I guess, implementation again. It reads, thanks for sharing the real life demonstration. Can this experiment be put to production?
Yeah, production means if some institute like clinics, the large scale clinics wants to that problems, then they can run their our code and our algorithm, and they can generate their rosters. That much we can do for them, because but they need a commercial license of DWeb, because every 15 days they have to run their codes, right, to generate their rosters. So they
So,
need their own DWeb license, commercial license.
okay. So for the code that implements the current presentation, they can get in touch with you, Kunal, by email, right, which you
Yeah, yeah,
provided.
yeah, yeah. Sure.
But for actual use of the quantum computer, quantum processor from D-Wave, they have to acquire the time on that machine or the processor separately.
Yes.
Excellent, wonderful. Great. There was one question which is perhaps a bit elementary. It says, could the integration be used instead of summation for a generic solution?
Yeah, or integration and summations. It's a mathematical part of notations. It's all the same thing. Uh,
I suppose the technology platform also would determine, right, what's going on. So as Dr. Kunal had said, so I'm just going to jump in and say a few words, Kunal, about this, because
yeah,
this
yeah,
has
definitely.
mathematics.
You can add it as a mathematician, right?
Right. So the as Dr. Kunal, Arindam, and Asmita had mentioned, the quantum annealing platform is suitable for solving combinatorial problems, right? And these are discrete problems, and they manifest. If you want to think in terms of mathematics or the nature of the problem, they're discrete problems. So they come in like discrete packs, like based on integers and whole numbers rather than real numbers. So typically you see integration concepts arise when you're dealing with continuous variables, right? Uh, so that is not the case at the moment with D-Wave's architecture. It's specifically built for combinatorial optimization problems. But certainly when you do theoretical work and you for some reason wish to, for example, study what happens when you move from discrete to continuous variable, of course, integration would be the right thing to do. And of course, you'll have to make a choice of the measure, right? Is it Riemannian integration or Lebesgue integration? But that's a separate story. And I'll leave it at that, I guess. Excellent. I guess we have maybe time for just one quick question, if I can find one. Here, let's see. So I'm looking for a really quick one that we can address.
I have a question, Faisal.
Yes, please go ahead.
Yes, I think the question is how easy it is to change the constraint and implement, and how the performance is affected in D-Wave. Is it easy to change the constraint and run the result quickly for this sort of algorithm?
One thing that you mean that the constraints are defined during the problem description, right? When you have a problem description, then you have defined the constraints. Now the value you want to change, is it the question? Then it is a matter of just time, because for the value of b you can put the 6 or you can put 8. That is as per your system. Maybe the apart from the COVID-19 scenario, if you want to do the 8-hour system, so there should be a 3 shift. So then you just put the shift hour is a 8 instead of 6. So it is just change the one constant time, and then your
Also,
yeah.
so will the Lagrangian factor will also change, right?
Yeah,
Like you're
yeah,
fine
yeah,
tuning
yeah,
it
yeah,
every time.
yeah,
So
yeah.
will the code also?
Every time you need to fine tune the particular Lagrangian value, because this is the heuristic part
Mm.
of that. selecting the Lagrangian value.
But if I want to add a new constraint, say complex constraint, so it depends on the constraint and
That will be that will be added with that equation.
uh, how easy it is to
Sorry.
do in this scenario.
Sir, easy means you just need to change the code of that part. Need to add those things because your Q matrix actually getting changed. Uh,
That's it, right? So
yeah, your Q matrix getting changed.
and the running time may be affected because of the constraint.
Yeah. Since if your dimension get changed, definitely running time will get changed. Even maybe the problem that embedding problem comes
Yes.
because we have taken very small number
Yeah,
of
most
in our
numbers. Yeah, that's
small numbers. But if you go for the large number, like I'm giving the 9.6 million variables problem, that is probably not suitable for 5,000 keywords.
that's what
So
I'm getting at. Yeah.
so,
Okay.
when the problem is a large, so then we may require larger qubits to fit in it because
Yep.
embedding is required.
Thank
Embedding
you.
manual
Mhm.
manual embedding is required.